Today, we're going to look at the following circuit, which is an RLC circuit where all parameters are 1. At time 0, a switch is flipped, which connects the circuit to a forcing function, which is a voltage that equals sine of t. And our goal is to find the current through the circuit I of t after time equals 0. So let's begin. We're going to apply the Laplace transform, but before we apply the Laplace transform, we need to just think about a few initial conditions. Note that just based on general principles, the voltage across the capacitor, it cannot be discontinuous. It must be continuous. And that is because the current through a capacitor is going to be C dV dt. So if the voltage across the capacitor has any weird jumps in it, this is voltage across the capacitor, this is time, that implies there's an infinite slope of the voltage there. And if there's an infinite slope of the voltage, that implies that the current through the capacitor is infinite there, which is impossible. You can't have infinite current, so therefore you can't have any discontinuities in the voltage. So, and the same reasoning also applies to inductors, because the voltage across an inductor is L di dt. The exact same reasoning applies, which says that the current through an inductor must be continuous. It can't have any jumps. So what does that say about the initial conditions? Well, the initial conditions, therefore, are pretty straightforward. Both the voltage across the capacitor and the current through an inductor must be 0 before the switch is closed, just because the circuit is open. And then once the switch is closed, then those quantities cannot have jumps in them, cannot jump up to something at time equals 0 for the reasons I just said. So therefore, those quantities also must remain 0 at time equals 0. So the initial current through the inductor is 0, and the initial voltage across the capacitor here is 0. Had those initial conditions been non-zero, then our Laplace transform of this circuit would have been a lot more complicated, but it's going to be pretty simple because they are 0. So let's apply the Laplace transform to this entire circuit here. That's going to give us, well, what is that going to give us here? Let's just draw it out. So the Laplace transform of sine of t is 1 over s squared plus 1. Perfect. The Laplace transform of a resistor is just a resistor. And then the Laplace transform transforms capacitors and inductors into resistors as well. But it specifically transforms capacitors into resistors with a value of 1 over SC. Here, C is 1 farad, so it's just 1 over S. And again, this would have been a little bit more complicated had there been initial conditions. You would have had to incorporate those here. So this is pretty simple with those 0 initial conditions. And then it also converts inductors into resistors with a value of SL, S times the inductance. Here the inductance is just 1 Henry, so that gets rid of the L. And because the initial condition there was 0, it's also, you don't have to include anything else. So this is going to be the Laplace, the circuit in the Laplace domain. So let's try to find the current in the Laplace domain using Kirchhoff's voltage law. So Kirchhoff's voltage law tells us that the sum of voltage rises and falls over a closed loop is going to be 0. So let's go through this loop and add up all the rises and falls and set that equal to 0. So we go through the voltage source. We're going through the negative to the positive end, so that's going to tell us that this voltage is going to be a voltage fall of equal in magnitude to this here. Then we're going to pass through this resistor here in the direction of the current, as I've defined the direction of the current. So therefore, that voltage rise is going to be 1, the resistance times the current, so that's going to be 1 times S. Same thing through both of these resistors. We're going to keep going through this loop, keep traversing through the loop. Through this one, it's going to be a voltage rise of, it's going to be a voltage rise of 1 over S times I. And then here it's also going to be, we're going through this second resistor. That's going to be a voltage rise of this. And then finally, this all has to equal 0 because we've closed the loop. We've gotten back to the node we started at, and the node we started at was ground. So boom, this is our equation. I'm going to move this term to the right-hand side of the equation, and then I'm going to factor out an I from the left-hand side. So I'm going to get what am I going to get? I'm going to get 1 over S plus 1 plus S equals 1 over s squared plus 1. Then I'm also just going to multiply both sides by s. So that's going to tell me that that's going to multiply this by s. That's going to be this now. Boom. Goes s over s squared plus 1. Okay, and then finally, let's just isolate I of s. So I'm finally just going to get that I of s equals s all divided by s squared plus s plus 1 all over s squared plus 1. That's just moving this from the left-hand side to the right-hand side. So this is going to be my final expression for the current in the Laplace domain. And then I just have to take the inverse Laplace transform to find my final solution. But before I can take the inverse Laplace transform, I have to get this into a nicer format. I have to use partial fractions, and I just have to put it into a nicer format so that I can use my Laplace transform table. You can look one up online if you need to get a refresher on the Laplace transform table. So I need to convert this using partial fractions into something that looks like, into something that's going to look like, oh, actually, let me just do this on the second board here. So I want to convert something that looks like this into a fractional decomposition that looks like this. And you're probably wondering, well, why do I have as plus b in the numerator and not just, a? Why is there a first degree polynomial in the numerator? Well, that's because I have second degree polynomials in the denominator. So generally speaking, when doing partial fractions, you always want to have degree n minus 1 in the numerator. So if this is degree 2, I have degree 1 polynomial in the numerator. So this is going to be my decomposition. I want to convert this into something that looks like this. So let's go ahead and multiply through by the denominator of the left-hand side. That's going to get rid of all the division in this problem. I'm going to be left with this times this plus this. Boom. Okay, and then let's go through and just FOIL all this stuff out. So that's going to be as cubed plus as plus bs squared plus b. Then this is going to be cs cubed plus cs squared plus cs plus ds squared plus ds plus d. Okay, I think that's right. Yeah, that actually looks pretty right to me. Okay, and now let's go through and group like terms. So I'm going to circle all the coefficients of the cubes, which is going to be a and c. I don't see any cubes on the left-hand side, so I know that those coefficients must add up to 0 to get rid of all the cubics in this. In this equation. Now let's put a box around the coefficients of the squares. So I see a b, I see a c, and I see a d. So I got b plus c plus d, and then I don't see any squares, s squareds, on the left-hand side, so these also must add up to 0 and get rid of all the squareds. Let's put a triangle around the coefficients of s. I see an a, c, and a d. I think that's right. Okay, perfect. So all of these then, I see an s, a 1s on that side with a 1 in front of it. So these all must add up to that 1. And then finally, let's put a cloud around the constant terms. I see a b and I see a d, and I don't see any constants on the left-hand side. So that's going to be, I know that b and d also have to clear the whole equation of constants by adding up to 0. This is a really simple system of equations to solve. I know that b plus d has to be 0, so that means that b and d have to cancel each other here, which implies that c is 0. If c is 0 here, that implies that a is 0. And then finally, because I also know that, well then this is also easy. If a and c are both 0, boom, boom, then this implies that d is 1. And if d is 1, that implies that b is -1. So now I just have decomposed this, and I've decomposed this into the partial fraction as plus b, which is just going to be -1 all over s squared plus s plus 1. And then cs plus d, which is going to be just 1 all over s squared plus 1. Perfect. This is my fractional decomposition. I'm almost ready to take the inverse Laplace transform of this, but I just have to manipulate this one more time, and I'm going to do that by completing the square. So there's an invisible 1 here, and to complete the square, I was always taught to take that invisible 1, divide it by 2, and then square it. That's going to give me 1/4. And then in this denominator over here, I'm going to add s squared plus s. I'm going to add a 1/4, but I'm also going to take away 1/4 so that, I'm not doing anything. Convince yourself that what I just did is mathematically legal, but because I'm just adding 0. And then I can use, what is the term I'm looking for? Completing the square. I can turn this into a perfect square, which is just going to be s plus 1/2. And then 1 minus 1/4, that's just going to turn into 3/4. Okay, perfect. So this is what I'm left with by completing the square. Let me just bring the second term over here too, which is 1 over s squared plus 1. Very nice. Okay, I'm so close to being able to use the inverse Laplace transform on this now. There's just a few more considerations I have to do. Let me just bring this up here. So my goal is to be able to do the inverse Laplace transform on -1 all over s plus 1/2 squared plus 3/4 plus 1 over s squared plus 1. I want to be able to take the inverse Laplace transform of this. I'm so close. I just need to remember that the Laplace transform of sine of omega t is going to equal omega all over s squared plus omega. That's a really important identity I need to know. And then I also just need to remember that the Laplace transform of f of t times e to the negative c of t is going to equal f of s plus c. This is the shift formula. So these two formulas, I'm gonna use these two things from the Laplace transform table. Again, look it up if you don't have one in front of you. Look it up, Google Images. I'm going to use these two lines from the Laplace table to work on this little guy here. So I'm so close to being able to invert this in terms of some sort of sign. I can take care of this thing with the shift formula, but notice that I have omega and omega squared here. If I want to do that, I need to have the square root of 3/4 in the numerator. So let's just change this term a little bit by putting the square root of 3/4 up there. So that's going to be √3 over 2. And then I'm going to have this plus 3/4 plus, again, this term is all good. That one's ready to be inverted. But then that's not, I also got to, I can't do anything mathematically illegal. So this is now what I'm working with. This is what I want to invert. Can take some time, pause the video to convince yourself that what I did to this expression is totally mathematically legal, that I have not changed the final value of the numerator from -1. Spoiler alert, everything is mathematically legal, so let's now go ahead and just take the inverse Laplace transform of this. So if I just ignore this, what's right here, if I just pretend that this is an S, this is a perfect Laplace transform of sine, where my angular frequency omega is √3 over 2. Perfect. Okay, that's pretty nice. But then I have to take into account this shift here, which is going to tell me that I also have to multiply my final answer by e to the -1/2 t. I have to take into account the shift of 1/2 with an exponential. And then this term over here, this one, that's super easy. Recall, originally, 1 over s squared plus 1, that's just the Laplace transform of sine. So let's just go back, invert it, and go back to sine of t. Perfect. And then the last thing I want to do is I just want to make sure I don't have a radical in the denominator. So let's multiply by √3 over √3. And then I'm also just going to flip these terms. And finally, I'm going to find out that I of t is equal to sine of t minus 2 root 3 over 3 e to the negative 1/2 t sine of root 3 over 2t. This is my final expression.